Afternoon, everybody.
Afternoon.
Hello.
A little bit of a late start. Thanks for being patient, waiting for me.
No problem.
Let's see here. I don't know how many homework questions we'll have today. I'm just working on posting. Forgot to post a practice document. So we're just going to post that now. Let's see here. Okay. Almost ready. And if you want to download the practice, I'm going to post it right now under the Unit 4 folder. And let's see here. New upload files. And let's see if I can find it. Okay, there it is. Add, and it should be right after the 16.5 videos now. So if you want to follow along, I don't know if we might have plenty of homework questions, but in case we need it, it is ready. So speaking of homework, let me get into those homework questions. 16, working on 16.5. Oh, let me pull up the updated schedule. I posted this, but I don't think we had a chance to talk about it together. So updated schedule for today. I did ask you to watch all the way through 17.2, but I still have the second video to make, so I'll do that one later today. So hopefully you've watched 16.5 and we can go over questions from that. 17.1 if you have them. Tuesday we'll finish up 17.2 and then we'll have 16.5 through 17.2 homework due, and then we'll talk about 17.3. And then we're going to continue on next week into 17.4 and 17.5, but those will not be on the exam. The exam will only go through 17.3. So we're going to be a little bit off here. We're not going to have any homework due for 17.3 because we just don't have that lag. We don't have time to have that extra lag time. So that exam will be through 17.3. And then we're going to do some of these sections, we're going to do a little bit briefer. So you'll see in the notes, I've been getting some advice from some colleagues. There's going to be stuff in the notes where like, well, we're just going to skip this example, or we might not do this proof because the proof, we just don't have time for proofs at this point. And I don't want to have this long video that you don't have to watch just because it's about a long proof. So you'll see we're going to try to cover everything. That's the goal, but a lot of the stuff will be briefer than it would be otherwise. Yeah, and then we'll finish up that last Monday. I will release the final exam, and then that'll be it. We're not going to hold our Monday, Tuesday class. It just seems like a short turnaround to give you like basically Tuesday night and Wednesday. So we're going to try to answer all of our questions by the end of the day on Monday so that you can have finals. Like Tuesday and Wednesday, you can just devote those 2 days to your final. So that's my plan. That's my plan anyway. Are there any questions about the schedule or about like kind of like to do like a big picture semester plans? Any questions about any of that? All right, be sure, just let me know if you do. Shoot me an email. I'm trying to kind of winging it here. I think this will be a reasonable plan given what we have, but we shall see. Let's do some homework questions then. Does anyone have any homework questions we're working on 16.5, cylindrical spherical coordinates, and then we're also working on 17.1 vector fields. Any questions on either of those two? 17.1, number 27. All right, let me pull that up here. Let's see, exercises. 27. I'm going to snip the whole section of problems here because it has instructions at the top. Okay. Oh. Zoom in a little bit. It's weird how I feel like usually when I paste it in, it's like super big, now it's super small. Okay. So we have a vector field. This is the one we're working on. We have a vector field, just the radial field xy, and then a curve C, circle, and we're trying to determine the points, if any, along the curve at which the vector field is tangent to C, determine the points, if any, along the curve C at which the vector field is normal to C, sketch C and a few representative vectors of the field on C. Michael, any particular, like, do you want to just jump in, do the whole thing? Do you have a particular question about it?
Yeah, I'm just confused about like finding like vectors that are normal to it and then that are tangent. Like I have kind of an idea about it, but I just wouldn't know.
I almost want to do, let's do C first.
Yeah.
And I think that might help us. So the path is just a circle radius 2. Circle radius 2, that's our path. And then let's draw some unit vectors, or not unit vectors, let's draw some vectors that are on C. Okay, so I'm gonna just pick a point here. Let me draw those. I'm gonna draw those in red. So like the point out here is at 2, 0. That's its coordinates. So the vector from there, the vector here would be 2, 0. You just make a vector out of a point. So that would go 2, 0, right? It'd be a length 2 to the right. What if I go on the y-axis? That would be the point 0, 2. And so if I make a vector, it needs to be 0, 2. If we pick a point at 45 degrees, if you're on the unit circle, it's square root of 2 over square root of 2. Or sorry, square root of 2 over 2, square root of 2 over 2, but now I'm doubled that. So this would actually be square root of 2, square root of 2. It would be at the same x and same y. We could pick something in the negative, maybe the negative x here. Those coordinates there are negative 2, 0. So the vector would be negative 2, 0. Negative 2 in the x direction, 0 in the y. So just by inspection, we haven't proven anything, just by inspection, where does the field appear to be tangent to C? Where does it appear to be normal to C? You don't have to answer that, Michael. That's kind of an open question. Anybody have any thoughts about that? Do you see any of my vectors that appear to be tangent to the curve? What about normal?
No, they all look normal.
Don't they all look normal? So it seems like none of them are tangent to C, and they're all normal to C. Well, I guess we need to know a little bit more about the vectors and the curve itself. So trying to figure out how to ask the question. I mean, how do you show that a vector is normal to a curve? Is a question. How do you show that a vector is normal to a curve? Or parallel, pick one, either one, but I think that's going to be the key. If we can understand that, then I think we'll be able to answer the question. Anybody have any ideas about that?
Well, isn't it just like it's gradient or something?
Okay. The gradient of the curve. Okay. So if we do the gradient of C, we're kind of doing like a constraint function here. So the gradient of C would be 2x and 2y. If we make, and we shouldn't really call it C, because C is an equation. You can only do a gradient of a function. So let's make a new function, call it g of xy, which is x squared plus y squared minus 4. And so what we're doing here is essentially saying the gradient of g, which is 2x, 2y, is orthogonal to g, but C is just one level curve, is when g is equal to 0. So you're right, Michael. I'm just kind of trying to make sure we have the abstract reasoning behind it. The gradient of g is orthogonal to the curve C. It's just not technically correct to take the gradient of an equation. You have to have a function. You take the gradient of a function. So that's the gradient. And that gradient will be orthogonal to this curve. But our field F is just xy, which is clearly just double the gradient. So F is also orthogonal to C. Always orthogonal to C. And I guess you can answer A then too, because if it's always orthogonal, then it's never parallel. It's never tangent. I don't know. I think that's probably how I would answer that. Does that make sense and help on that one, Michael?
Yeah, so it would never be tangent at any point. It's
Nope.
just, and the reasoning for that is to turn the curve into a function, take the gradient and see if there's any sort of like relationship between F and then that function.
Yeah, you could say that F is tangent to C when it's when F is perpendicular to the gradient.
Right,
So,
so
right,
the dot product would equal 0.
correct. And let's do that. It would be x, y, dot product with 2x, 2y, and we get 2x squared plus 2y squared. If we set that equal to 0, that's never true on the circle. It's only true at the origin, but the origin is not on the circle. So that would be a formal way to do it too. I mean, for me, the argument is, well, if it's always orthogonal, then it can never be parallel tangent.
Right.
But this is a good argument too. And that's the argument that the textbook uses. They use that one. Good, good. Any other homework questions? I have 17.1 and 16.5 up here. We're skipping everything in the middle there. 16.5, Rudy asked about 16.5, 41 and 51. Get a little bit nervous. Some of these are not easy. Oh boy. Let's see here. Okay, let's start with 41. Give myself some extra workspace there, a little too much. Okay, there's 41. And we are supposed to use spherical coordinates here. We're supposed to use spherical coordinates. So the key here, rho squared is x squared plus y squared plus z squared. And then if you recall, in terms of the coordinates, rho is the distance from the origin. If you kind of cast a shadow down to the xy plane, theta is the angle there. And then phi is the angle from the positive z-axis. So if we have a unit ball, what that means is we're integrating over a sphere that's terrible. It's supposed to be a sphere. So it's a sphere radius 1. So that's what we're integrating over. That's the region that we're integrating over. So the reason why that's important is because, I mean, it's easy enough to just say, well, x squared plus y squared plus z squared is rho squared. And dv is rho squared, sine phi, d rho, d phi, d theta. You're just substituting that in, but you have to know the bounds. That's why you need to know what is the unit ball, because you have to know what the bounds are. But integrating over the unit ball, rho goes from 0 to 1. Start at the origin, go out to the edge. I guess we're doing phi next. Doesn't really matter. But phi goes from, if you go over to the drawing again, phi starts at 0, the positive z-axis, and then swings all the way through to pi. 0 to pi. And then theta is going to go all the way around the xy plane. That's 0 to 2 pi. All right, Rudy, is that helpful so far?
That's what I got so far.
Okay, all right, good. All right, so let's simplify. That would be rho to the 5th, but then there's already a rho squared, so rho to the 7th, sine phi, d rho, d phi, d theta. Let's see, integral 0 to 2 pi, integral 0 to pi. Let's integrate the rho, so 1/8 rho to the 8th from 0 to 1, and then we still have a sine phi, d phi, d theta. And then integrating 1/8 p to the 8th, sorry, evaluating that at 1, subtracting, evaluating it at 0, that would just be 1/8 sine phi, d phi, d theta. 1/8 integral of sine phi would be negative cosine phi from 0 to pi. Negative 1/8, I'm going to put the negative with the 1/8, and then we have cosine of pi minus cosine of 0 d theta. let's see, cosine of pi is -1. Cosine of 0 is 1. So that's -2. So I guess we just get 1/4 theta from 0 to 2 pi, which will be 1/4 times 2 pi. So pi over 2. Looks like what it is anyway. So did that get you to what you needed there, Rudy? Is that one okay?
Yeah, yeah, it looks like I screwed up around like cosine of pi minus cosine of 0 is where I screwed up.
Sure. Lots of opportunities to get stuff wrong there. Think about how many different computations we did there. That's a lot of stuff there. So, all right. And then 51 also. So let's take a look at that one. 51. Oh, man. Who picked these problems? This looks rough. Yikes. Okay. Woo. The solid outside the cone phi is equal to pi over 4. So that's at an angle of pi over 4 and then sweeping all the way around. So that's the cone, phi equals pi over 4. And then inside the sphere, rho equals 4 cosine phi. You can kind of see on the picture. I can prove to you why that's true. If you multiply both sides by rho, and then simplify that, let's see, rho cosine phi. I need my notes here. I haven't done the spherical coordinates in a while. There's the integrals. Oh, we just need the coordinates though. There we go. So rho cosine phi is z. So if we, I'm actually, why am I changing software? I'm already here. I just need to go to a different, back to where we were. And so we have x squared plus y squared plus z squared equals 4z. And if you complete the square on this, x squared plus y squared plus z squared minus 4z, and then add 4 to both sides, you get x squared plus y squared plus z minus 2 squared equals 2 squared. And you can see, hopefully that's obviously the sphere there for you. Maybe not if you haven't practiced with those sphere equations, but they gave us the graph. We did not, this was unnecessary. We didn't need to do this, but just to kind of verify that, yes, indeed, this is a sphere. It's centered at 0, 2. Its radius is 2. Okay, we want to go outside the cone and inside the sphere. So essentially we're looking for these bottom areas there. Okay, so let me look at it from the side. X, Y, and then you have these. And then of course they do swing around, it's 3D. Okay, I think I have the bounds set up in my head here. We want to find the volume. The volume is just going to be the triple integral over the region dv. So the function will just be the rho squared sine phi, d rho, d phi, d theta. So just the standard dv for spherical. But now we need to know, where does rho start and end? Where does phi start and end? Where does theta start and end? And I feel like this is similar to one we did wrong. Do you remember that one? I feel like that was, where was that? I can't remember where that one was. Maybe it was, maybe somebody asked about it last time. Can't remember. I just remember there was one like this here, 49, right? We set that one up wrong. And so I think, let's see if we can do this one right the first try. So, I mean, the easy one is theta because we're going all the way around. So theta is from 0 to 2 pi. Okay. That's easy. Does anyone have any thoughts about rho or phi?
For phi, I'm pretty sure it starts at pi over 4, but I don't know where it ends.
Okay, I agree. It does indeed start at pi over 4. This is why I wanted to look at it from the side to help see that. Some of this, I feel like I need to zoom in here. I don't know if I can do this. Can I grab this and like make it bigger? Huh. Okay. That was cool. All right. And just have a little too much here. So this is like, still it's either the X or the Y over here. But if we imagine a little ray going out from the origin, so here's our little sliver, and we're going to imagine it sweeping, and it starts at pi over 4. It gets smaller and smaller and smaller and smaller and smaller. And the question that we're trying to ask now is at which end, at which angle would that smallest one be at the very bottom? Because I agree that it starts at pi over 4. Does anyone have a thought about that, about what that bottom angle would be?
Would it be pi halves?
It would, yes. And I think to your question in the chat, I don't think it's necessary. I don't think this needs to be 2. Because the phi equal pi over 4 is basically just cutting off the top and telling us where to start. But it's the same, but the rho, this is the key here, maybe we should have done the rho first. Rho goes from 0 out to the hemisphere, or out to the sphere for cosine phi. Every time, rho starts at 0 and it ends at rho equal 4 cosine phi. So I think this is it. I think it's just a single integral.
So wait, how did you determine that it ends at pi over 2?
Let me see if I can do another drawing. So much of this is, it's such a new coordinate system, and so it's just kind of takes a while to wrap your head around it. Let's look just at the first quadrant, right? It's just that portion of the sphere. And so again, we're imagining, let me go to red again. We're imagining rho goes from 0 out to 4 cosine phi. And then we're sweeping out, we're starting, the top one here is at phi equal to pi over 4. And then as you go, like here's phi equal pi over 3. We're getting larger and larger, but the last one is kind of like where you're straight across. And that's pi over 2, right? Angle from the positive z-axis. And you go beyond that, there's nothing, there's no volume beyond pi over 2. Pi over 2 would be straight across. Once you go beyond pi over 2, there's no volume.
Okay, I think that's where I was confused.
I don't know if that,
Because I actually thought that like at the bottom, that's where pi is, but
yeah, the only way you'd have pi is your shape. We did one kind of like this, but again, just looking at it from the profile, your shape would have to extend. So you'd have a rho going out that would be below pi over 2. Your shape would have to extend below the x-axis for you to have phi be more than pi over 2.
okay.
Yeah, if your shape's above the x-axis, your phi cannot pass pi over 2.
Got it. I think that's just where I had trouble with this one.
Yeah, and again, like it's a new coordinate system and you're trying to wrap your head around this, like it's a fair question.
I did have more of a general question too that's kind of attached to this.
Sure.
Why is it that phi is never negative?
just the definition.
Okay.
That's just how we're going to define phi.
Okay. Got it.
Yep. Like you can imagine defining a point down here and saying phi is, what, like there's different ways to imagine those points over there.
Mhm.
So just the way we're going to define this coordinate system is we're going to say phi is from 0 to pi.
Okay.
Yeah.
Got it.
Yeah, good, good. We didn't finish this one. I don't know if anyone has any additional questions on 51.
Yeah, would you multiply everything by 2 just because there's like 2 sides to it?
You could, that's not going to help you.
No.
So the 2 sides, do you mean like in my drawing over here?
Yeah, because like everything on the right side is, well, it would be the same on the left, right? That's what I'm thinking of. So that's why I was
Yeah.
like, multiply it by 2.
No, so that's already covered. That's already taken care of, because really what it is if I look at this, the picture, the second picture, if I look at just that integral, I could write that integral as an area. It's just area. And it would be the integral rho goes from 0 to 4 cosine phi. And then phi goes from 0 to, or sorry, from pi over 4 to pi over 2. That would just be area. And then to get volume, all we do is rotate all the way around. We
Okay.
just kind of, so it's all, the volume then is taken care of by the 0 to 2 pi d theta.
Got it.
Yeah, the drawing might not be a great one up there with both sides. I was trying to like just visualize if I looked at it in profile, that's kind of what it might look like in the cross section of it. But it's really only that first octave, first quadrant that really matters. All right, good question. Any other questions on 51? All right, other homework questions, 16.5 or 17.1?
Can we go back to that number 49? The one that we were trying to figure out last time?
Yeah, do you want to just start from scratch? I feel like we did that poorly at the end of class. Or should we just reflect back to our notes?
Yeah, I think I have it figured out. I just want to like kind of make sure.
Yeah. So here's from the end of class. Oh, it's like a delay on my Zoom here. So this is similar to 51. So you have a solid bounded by the sphere, rho equals 2 cosine phi, and then the hemisphere, rho equals 1. And let's see here. Well, theta is easy. Theta is going all the way around 0 to 2 pi. We want to go, yeah, this is where we struggled. Is this, I want to start from scratch because I'm trying to figure out what we did, and let me just try again here. I think that might be best. Especially now since we've had, I feel like we learned a lot from that one, and then now we just did one that was similar. I think I kind of want to look at the cross section again. Just looking at the XY axis and the XY plane, I should say. And there's the hemisphere, rho equal 1, and then it's cut off by the other sphere, Oh, sorry. Which was rho equals 2 cosine phi. And I think this one, I don't think my notation is correct here. I have like an equal sign here. I think we meant plus here. I think that'll make more sense. I think this one we do need two integrals, because if I draw my rho from the origin, okay, that's fine, goes from 0 out to 1, 0 out to 1, 0 out to 1, but then once I pass this point, then down here, rho goes from 0 to the rho equal 2 cosine phi. So I think we do need to split this one up into two different integrals. There's one part of it is like an ice cream cone. And then the other part of it is like we just did in Rudy's problem. It's the little sliver on the bottom. And of course, it's all three-dimensional, but okay. So I think that's the idea here. We'll get the cone will be the bulk of the volume. It's not really a cone, not like the geometric cone, but like the ice cream cone. The ice cream cone, because it's a cone with a sphere on the top. So it's like an ice cream cone, not the actual geometric figure. And then plus the triple integral for the bottom. I need more space. And d theta is usually kind of boring on these. So that's 0 to 2 pi, that's fine. Okay, so let's do rho. For the cone part of it, rho just goes from 0 to 1. And then for the gold sphere part of it, rho starts at 0 and goes out to the sphere, 2 cosine phi. So we go back up to my drawing here. For this portion, rho goes from 0 to 1. And then for the bottom portion here, rho goes from 0 to out. You can barely see the little sliver there, but rho goes from 0 out to the sphere. Okay, any questions about the rho bounds? Maybe. Okay, for phi, then we're going to split it up into two. We're going to start with 0 to something that we'll have to figure out. And then the second one is that same something. And then just like Rudy's question, it's going to go all the way to pi over 2. There's nothing below the xy plane, though, so it's not going to go past pi over 2. So it's going to go, the first part's going to go from 0 out to wherever this part is. All right, it's going to start at 0 and then end up here. And then the next one's just going to go from there to pi over 2. All right, wherever that angle is, then it's going to be all the way down to pi over 2. So I remember doing this. Do you remember how we figured out that angle?
Yeah, just set the rows equal to each other.
Yeah, that's correct. So to find phi of the intersection, you set row 1 equal row 2, basically. You set the two, set the two spheres equal to each other. You have 1 equals 2 cosine phi, 1/2 equals cosine phi. Since phi has to be between 0 and pi, then phi must be pi over 3. And so that's our mystery, our unknown angle in here is pi over 3. Yeah, I don't get their work at all. They like, I don't know, I think ours is better. Our reasoning is better. Their integral is simpler. They just get like a single integral, but it makes some big leaps. They're like, I don't really understand those leaps. So we're not going to do them. All right. So does that help on that one, Michael, the setup?
Yeah, that's what I had. I just didn't
Right.
evaluate it. So
Yeah, did you want to evaluate it, or did you just want to make sure like where it all came from?
no, yeah, I just wanted to make sure that that was right.
Yeah, I think that's where we ended up last time too, but it was chaotic at the end of class and we like did it wrong, and so this is better. This is good. Okay, good. Any other requests from homework? Okay, I'm not seeing any. Last call. Okay, so why don't we then take a couple of minutes, see, I wasn't sure about how much workspace to leave on these. I kind of glanced at them quickly, but while we were working here, before class, and I'm like, these look like a little scary, so I don't know if we might just be able to do one. So I loaded right at the beginning of class here, I loaded in D2L under Unit 4, and there are some 16.5 extra examples there. So I just picked a few from the homework. Kind of these look similar to the assigned ones, and they're not on the recommended list. They're not on the required list. So these some additional ones to do. Okay, so first one here, we're just going to do this triple integral, and they're nice enough to give us the drawing here. I guess we have, like, let's say this is on the test. You have lots of decisions you need to make, but there's one major decision you have to make if you're going to do a triple integral. What is that decision?
What coordinates to use?
Correct. You have to pick a coordinate system. Do I want to do rectangular? Do I know how to do this integral? The answer to that question actually is no. Well, maybe it'd be like an arctangent, maybe. The first one with z is going to be fine. The z goes from 0 to 2, and so that's fine. But then you're going to have the integral of 2 over 1 plus x squared plus y squared dy, which is kind of like an arctangent. I don't know. Seems bad. If you look at this region, you can see a little bit more clearly, like, hold on, if I look at this from above, x, y, it's a semicircle. The region that I'm integrating over is a semicircle. So we should use which coordinate system then?
Cylindrical.
Yep, cylindrical. Really, I think I hinted at this on Thursday. Primarily the only time you use spherical coordinates, we could make up problems that use spherical coordinates, but typically it's when the region you're integrating over is a sphere centered at the origin. That's when you use spherical coordinates. So this one we're going to use cylindrical. Okay, so we're going to do -3 to 3 integral 0 to, oh, okay, I guess we have to substitute in here, right? R squared cosine squared theta. And then we have the integral from 0, actually, hold on. No, that's not a bad idea. Sorry. So I think what I'm going to do is let me do the first integral. This is how I usually do these cylindrical ones, is just do the first integral. You don't need to do it this way, but if I do the first integral, it's just z over 1 plus x squared plus y squared. And z goes from 0 to 2 dy dx. And then it's just 2 over 1 plus x squared plus y squared dy dx. And then now I was like kind of lost my mind there for a moment. I was trying to like direct substitute what x and y are equal to. No. We'll maybe do that in the integrand and call, oh, x squared plus y squared is r squared. That's fine. When I change my when I change to cylindrical coordinates, the dy dx becomes r dr d theta. That extra r is always there. It's just part of the dA. Or if you changed it from right from the original triple integral, it'd be part of the dv. And then I'm not going to try to substitute into the bounds. That was a mistake. What I should do instead is look at the region in polar coordinates and decide what does r vary from, to and from, and what does theta vary to and from. So r just goes from 0 to 3. Origin out to the edge, it's radius 3. And then theta, oh, we don't actually go all the way around this time, just 0 to pi. Only goes halfway around. And for me, the only reason why I do that is sometimes I struggle wrapping my head around what's z, what do I leave, how do I change these bounds. So sometimes it's better for me to just like get rid of the z. That might not always be possible. So sometimes you might have to set it up initially. We could have done it initially as well. Oops, we're getting a 0 to 2 here. So there's the original integral, and the way we would set this up initially, it's basically the same. 1 over 1 plus r squared, and then dz dy dx becomes dz r dr d theta. And then we still need to look at the x and y bounds and decide based on the x and y bounds what the corresponding polar coordinates would be. Z is still from 0 to 2, and then you'd still get the 0 to 3 and 0 to pi. So I don't know if it's easier to integrate the z out of there first or not. We're always going to end up at the same integral. You're still going to get to this integral. It's pretty easy from there. Well, we can keep going here, but are there any questions on that conversion? All right, let's see if we can finish that one up then. I'm going to take a leap of faith here, but do you see the 2r dr? And if I did a u equals 1 plus r squared, it would just be perfect. The du would be right there, 2r dr. So it's just du over u, so it's just natural log absolute value of u. So it's just natural log absolute value of 1 plus r squared. In fact, you don't even need the absolute value here because 1 plus r squared is never negative anyway. So I'm just kind of mentally saying u is 1 plus r squared. Du is 2r dr. Oh, it's perfect. So it's natural log absolute value of u. So I just kind of did that all mentally. And let's see, that would be natural log of 10 minus natural log of 1, which is actually just natural log of 10. That's natural log of 10 then times theta from 0 to pi. So pi times the natural log of 10. Any questions on finishing that one up? Okay, let's try to do one more here and then we'll call it a day. Let's do a spherical one. Ooh, let's try to set up. Oh, no, I don't want to do that. That one's already set up for us. Let's set up 43. It's not set up yet. We're going to do, you can see, same question as we have to do spherical coordinates, or we have to decide a coordinate system. Here, it's the solid between two spheres. So dead giveaway, we're going to use spherical coordinates. Okay. Triple integral. Those were terrible. Triple integral. dv, we're going to do rho squared sine phi d rho d phi d theta. And then x squared plus y squared plus z squared is rho squared to the 3/2. I feel like I do this a lot. Let's just look at those. I don't know, can you visualize this? Like, if I were to slice this, whatever this d is, this solid, if I were to slice it right down the middle at like the y-z plane or the x-z plane. Sorry, I'm not trying to do x and y. I'm trying to do the xy plane and then the z-axis. That's what I'm trying to graph. So if I slice it vertically right down the middle, what is it going to look like?
It'd be kind of like a ring, sort of.
Yep.
I thought it'd be more like a ball with a hole in the middle.
Yeah. So three-dimensionally, this whole solid is a ball with a hole in the middle. If we slice it and just look at the cross section, it would be like a ring. But physically, the whole thing is indeed a ball with a hole in the middle, like a hollow core. Yep. So if we just look at just the cross section though, because I was going to use that to help me and visualize, well, rho coming out from the origin. Rho coming out from the origin starts at rho equal 1 and ends at rho equal 2. So it's just 1 to 2, d rho. All right, phi is the angle from the positive z-axis. So it starts all the way up at the top and then sweeps out all the way down. You see, to Rudy's earlier point, this one does have some stuff below the xy plane. So it will continue beyond pi over 2. It would go from 0 all the way to pi. And then finally, theta, we're going to spin this all the way around. So it's going to go, we're not going to spin it, but I mean, it does exist all the way around. It's a ball. So 0 to 2 pi. Honestly, that integral is easy. It's all, each integral itself is not fancy. There's a lot of stuff going on, of course, but setting up the bounds is the real challenge on this one. This is a good test level question, something like this, where like the integral itself is not crazy, but you really have to know what's going on and know the coordinate systems, know to choose, oh, it says sphere, I should choose spherical. And then know the coordinate systems to know how to set up the bounds. So you really show a lot by knowing how to do this problem. You've really demonstrated that you know not just how to do the integrals, but how to set them up. So this is a good test level question. Nice like way to demonstrate that you know these coordinate systems. Okay. I think I just want to set that one up if that's okay. Any questions on that setup? Okay, so it sounds like we're good. I am going to work on getting the 17.2, the last 17.2 video up for Tuesday, and then we'll turn in that homework for Thursday and then continue on. I'm just looking at my notes here. I don't know how to do everything with assessments for the rest of the semester. How to have the exam, like we're just not going to be able to have homework due on everything else. So we might, because even that, you know, that week we have 17.7, like I don't know that I will be able to get that homework back to you by Monday. So we'll kind of see how that goes. But definitely be working on the required, we are definitely going to have 16.5 through 17.2 homework due. We will definitely do that. We may have to see how the rest of this all goes. There was, last homework was supposed to be much earlier in the semester. Now it's like all the way up at the end, and I just don't know if that's feasible now that I'm looking at it. So watch the 17.1 if you haven't watched it, and then watch both 17.2. I'll get the last 17.2 video out pretty soon. And watch those for tomorrow, and we'll go over hopefully lots of homework questions tomorrow, some additional examples if we have time. All right, enjoy the rest of your afternoon. Get outside, it's beautiful out. I'll see you tomorrow.